Uh, I'm going to talk about the symmetric regularized long-way equation. This is an equation of this form here. Okay, this form here. And this equation was introduced by Seiler and Fester-Marcher as a model for the weakly nonlinear one-dimensional ion acoustic waves. In fact, also models charge space waves too. This equation have this equivalent form. For this system, I'm interested in three aspects. First, local well-posedness. Second, global well-posedness. And third, orbital stability for periodic waves. Okay? This system has four conservation laws. Note that this is the, okay, I'm going to call x h1 times L2. I'm going to call xx times x minus 1. Okay? Note that the x norm is conserved. Okay? Our first result is this. We have local and global well-posedness in hs times hs minus 1 for non-negative values of x, of s. Basically, our result is based in this work of Bona and Chekhov about the BBN equation. The principal ingredient for the proof of the local well-posedness is this lemma here. I want to call the attention on the definition or bar phi, so this form. And with this lemma, well, you know, you have to solve this integral equation. Here, G is given in this form, and here, my bar phi is exactly the same as Bona and Chekhov. Okay? Then I can use the result directly. The semigroup associated is this one here. It's fully transformed. It's given in this form. I want to apply the fixed point theorem in this space and with this norm, as you know. And it's easy to prove this inequality here for the semigroup. And using lemma 1 and the properties of x, you can prove this inequality here. Also, you can prove this. Well, and as you know, with these three inequality, you can apply the fixed point theorem and get a unique local solution for our system. Okay? Now, to obtain the global result, we also use another lemma proved by Bona and Chekhov. It's this lemma here. I'm going to use it for s between 0 and 1 and r equal to 1. Okay? F is going to be in H1 and G between in HS for S between 0 and 1. Well, the idea, basically, the idea is the next. Choose an arbitrary T, an initial data in X, and think these two, well, you can choose n big enough such this is satisfied here. And you define the two new initial data, U sub 0 tilde and V sub 0 tilde. Okay? With these two initial data, you can apply theorem 1 and you get a solution U tilde V tilde in this space. In fact, the time of the system of this new solution is bigger than T. Okay? that is because this inequality here. But okay, I have a solution in fact in T. Okay? Well, now I define this new initial data, and I consider this system here. Here you can apply again the same idea of theorem 1, and lemma 1 is useful to deal with this inequality here, and lemma 2 is useful to deal with this nonlinearity here. In this case, W is in H1, and U tilde is in HS, with S between 0 and 1. You get a local solution in a time capital L, okay? And what you do next is to prove that this solution, in fact, is global too. You do this finding an a priori bound for your problem. And as usual, you multiply by Z, and you integrate, and you can obtain this equality here. You have the Sobolev and Holder inequality to obtain this, and then you use Gromwald lemma. Remember that U tilde and V tilde are solutions for system 2. Then the H1 norm is conserved. In particular, you can bound this norm here, but the norm U sub 0 tilde and V sub 0 tilde. Okay? And you can prove that the solution is bounded, and you can extend the local solution for any time. And then you consider you sum these two solutions, and you take a solution on T. Since T is arbitrary, you get your result. Okay? Well, all these results are also valid for the periodic case. Okay? It's the same argument, basically. Then I have local and global solutions for the periodic and non-periodic case for this system. Well, the second part of the talk is dedicated to the system and orbital stability of periodic traveling wave solution for this system. I'm going to consider I'm going to consider solution of this 4, as usual, with phi and PC smooth, with fundamental period L. Thank you to Professor Angulo. He talked a lot about this. When you replace this kind of solution on the system, you obtain this system of EDOs, the nonlinear EDOs. In our theory, d sub 1 and d sub 0 are 0, okay? I'm going to consider only that case. Then you can replace the second equation on the first one, and you obtain this nonlinear EDO here. Okay, then we know explicit solitary wave solution for this equation. Then I can use the Poisson summation theorem to obtain periodic solutions. Or in fact, you can use the quadrature method also, but the Poisson summation theorem gives you the Fourier transform of the solution easier. Okay, for this reason I use it. Well, then you obtain this curve, a smooth curve, in fact, of periodic solution for your system. And phi is given in this form. This is the kinoidal, the Jacobi elective function kinoidal. Okay? Again, veta 1, veta 2, and veta 3 depends smoothly on C. And also the modulus K depends smoothly on C. Okay? You prove this using the implicit function theorem. Okay? Well, now you have a family of solution, okay? Well, the notion of stability is this, okay? Is stability in shape. consider your wave for any epsilon positive, you get a delta such that for every initial data here, this is the energy space. If the initial data is close to the wave, the solution emerging from this initial data is also close to a translation of this wave. Okay. Let me show you a graphic version of this. Okay, full screen. You have, well, I'm going to do the solitary case, okay? You have your wave there. You consider the orbit generated by this wave. And you, for any epsilon, for any tube you take here, there is a delta such that for any initial data in this neighborhood, the solution emerging from this initial data remains on that tube. Okay, this is the graphic idea of the stability and shape. Okay. Well, the idea, I use the classical ideas of Benjamin Bona and Weinstein, and more recently Jaime Angulo. The idea basically is to prove that the wave is a local minimizer of this functional here, subject to a restriction on V. Okay. Well, it's easy to prove that the wave is a critical point of this functional, defined on X, this X here, the energy space again. The second derivative is this linear operator. Look at the definition of L sub 0, is of this 4. And basically, and you know, as you know, you need that H have one single negative eigenvalue. 0 is also an eigenvalue and is simple, and the rest of the spectrum is away from 0. You have this. This is you can do this using the property of this operator and the minimax theorem, minimax theorem. Well, here you define this function. Note that this norm is equivalent to the X norm. You only have this quantity here. Okay, this is the norm L2, 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 and you have the derivative here. Well, you can prove that the infimum is attained for finite, for each t, the infimum is attained in a gamma t, for example. And you define this perturbation of the wave. You define C and eta. Okay? Well, using this fact here, this embedding, all this, you can prove this inequality here. And the main ingredient of the proof of the stability is to find a lower bound for this quadratic form here. Okay? And for this, you consider two cases. The first case is this one. This is restriction I talk about. And with this, you can obtain this here for all t between 0 and capital T. Using the Petrarch property of H and a convenient decomposition of C and eta, you can prove this inequality here. Then you obtain this inequality here, and the norm, this norm is equivalent to this norm here, the X norm. Note that you only have this constant here, okay? In H is of D4. Well, here you have everything you need. and you use the beta is uniformly continuous on this set. This function is continuous, and you can obtain a delta depending only on epsilon, such that if the initial data is close to the wave in this norm, you obtain this, that h of this quantity is less than epsilon. And what you do is to remember that the infimum is attained on this gamma. And this is exactly the definition of phi and eta, and this is less than epsilon. And you obtain your result for the more perturbations on from 0 to 10. But okay, you can get your result for any t positive using this fact, and using this other fact, you can prove, in fact, you can remove the restriction that imposed on V. Okay, this is more or less classical, and you can obtain your result. All these are some of the reference. This is the classic work of Bona and Weinstein. This is the work on where the system is, or the equation is proposed. This is more recent work of Bona and Checo about the BBN equation. Okay, I think that's all.